Okay, any questions before we get started today? All right, so today what I'm going to do is we're going to talk about determinants. So far what we've done is show you what a determinant is and give you a theorem that shows that you can span the determinant by any row or column, right? But here is something that will further help streamline and help us understand it. And I also want to give you some practical stuff, and I'm also going to give you some under the hood stuff that's going to be a theoretical and practical importance later. So let's start off with the theorem. And this was a big one right here. So I might call it how row operations affect. Let's look at A. So once again, we're talking about a square matrix, but we're talking about determinants here. And we and obtain determinant a row operations. So we've got three biggies, right? Three row operations. If B is obtained from A by row replacement, and remember what row replacement is. That means I add a multiple of one row to another row. Right? Then very groovy. The determinant doesn't change. So if I take a matrix and I add a multiple of one row to another row, the determinant of the new matrix is the same as the determinant of the old. This is very important. Number two, if B is obtained from A by swapping exactly two rows, then anybody want to guess what happens here? What happens if I take two rows, swap? Anything. I won't guess. You know, if you want to kind of figure out what you think might happen, think about a simple case first. What's determined that matrix? It's determined with one, right? What's the determinant of that? Negative. Everybody agree? Now you all are engineers. You make up crazy formulas, and hopefully bridges don't fall down. So what do y'all think? What happens if I swap exactly two rows? That's a good guess. But it actually just changes. And finally, yeah, he is obtained from A by replacing a row of say that I'm multiplying a row of A by the number A. Then determinant of B is equal to, anybody want to guess?
A is the determinant of A.
What's it? I think you got it right. What'd you say?
A is the determinant of A.
That is correct. You can see this happening here. Multiply that top row by 5, and in terms of determinant, 1 is 5, right? Okay. So let us use this for a moment to let's redo an example that we did last. Do a couple examples doing this. Yes.
On that last example, you multiplied the top row by 5, so wouldn't the determinant be 4? Back one.
No, it's just the diagonal element, 5 times 1. So remember, that was one of the last terms we had last time. If you have an upper triangular or a lower triangular matrix, then the determinant is just the product of the diagonal element, right? And actually, I'm going to do this. We can do the determinant 3 by 3. It's easy peasy lemon squeezy, right? But it's kind of a pain, right? Because it's 1 times the determinant of this little matrix, -4 times the determinant of 211 minus 32, plus 3 times the determinant of this. It's annoying. So here's another way to do it. Let's do row operations here. So I'm going to take this first row and use it to take out the use this one to take this out. So this is going to be minus 2 and a half, like minus 2 and a half, minus 2 and a half, and then comes 3 and a half, and 3 and a half, comes 3 and a half. What's that? I noticed, what did I do there? I did row replacement, right? So the determinant of that new matrix is the same as the determinant of the original, right? All I've done here is row replacement. I think that's all I'm gonna need to. Now I'm gonna use this one to take this out, so another row replacement. Multiply this by -16 and add. Multiply this by -16 and add, and when I multiply it by -16, that is -8, isn't it? Plus 11 is -69. Everybody okay? Now, tell me why I'm kind of done here. This is up to triangular, and so the product or the determinant of this matrix is -69. And all I did to get from here to here is row replacement, and none of those operations changed the determinant. So the determinant here is -69 as well. So this is kind of another nice way to do it. Let me do an example that I did last time. Let's find the determinant of this. The last time I did this by expansion about one of the rows or columns, basically a cofactor expansion. This time I'm going to do some row rotation. Matrix 17, 1, 5, 3, 2, 0, 0, 1, 0. 0, 1, 1, 0. 0, 3, 1, 0, 1. Found with 0, 0, 4, 0. And I am curious as to what this determinant is. Now, we worked this out at the end of last time, expanding about, I think if I remember right, we expanded about the second row. So let's do some row reduction. And basically, I'm going to follow the same strategy that I did before. I want to grab this and ground and get it down to a triangle matrix. Yes.
You swap through rows and you swap other two rows, so you go back to positive.
That is correct, right? So if you swap two rows, and then you swap any two other rows, it'll be back to the original determinants. So the first thing I'm going to do here is I am going to, and I'm going to pull a star here. Actually, the colors. What I'm going to do here, my row reduction. 0, 1, 2, 0, 0, 0, 0, 0, 3, 1, 1, 0, 0. So in my first step, all I've done is I've swapped the original rows 2 and 3. And I think that this is the only thing that I'm really going to have to do with this in the row replacement. Am I okay with that so far? So what I'm doing is, so I'll make this note here to know that the original determinant, this will have a different sign, right? Well, now what I'm going to do is I'm going to take this second row and I'm going to do this row here. 17, 1, 5, 3, 2, 0, 1, 2, 1, 0, 0, 0, 1, 0, 0. Multiply this by minus 3 and add. Minus 3 and add. Minus 3 and add. Minus 3 and add. And I'm going to leave this one alone here. And actually, I'm extremely fortunate. And in fact, I can tell you that the determinant is already the product of the diagonal elements. Determinant there. Because notice, I can now use the third row to take these two out below it, and then it'll be fine. Right? So, write that down explicitly. Zero, 0, 0, minus 3, 1. Multiply that by 5 and add. Multiply that by plus 4 and add. Nothing else changes. Right, okay. Now I've got it in another triangular form, so it's easy for me to pick off the determinant here. The determinant of this matrix is the product of diagonal elements. So that's negative 1 and 2. So the determinant of the original matrix should be 1. Yes.
Would you keep it like that, or would you? You wouldn't like row it, so. Completely.
There's no need to here, because all I care about is what the determinant is. And so once I've got it in this form, I'm good to go. Don't do any work. Be lazy like me. Emulate my laziness. Don't do anything that's not necessary to make your life move on to the problem. Yeah. It's probably diagonal. 51, 102. Oh, you know. Yeah. Other questions? Okay. So let me give you an example here. Suppose you reduce A echelon using only row swaps and row. Let me point out that this can always be done, because what's the matrix operation, what's the reduction operation that I've left out? It's multiplying any row by a constant. You don't really need to ever do that, right, to reduce it to an echelon form, because if you can swap rows, and if you can add a multiple one row to the other, you can always bring it to upper triangular form. Always. So you don't really need that. Then I can give you a nice little formula here. The determinant of A is equal to 0 if A is not convertible, which is equivalent to say has less than in pivots or it's -1 to the R times the product of pivots. If A is equal. And here R is number of row swaps used. So really, so this is kind of a nice little compact formula, if you will. The determinant of any matrix A, reduce it to echelon form, reduce it to upper triangle. Then the determinant is the product of the pivots, which if you look back to this example here, the product of the pivots is 17 times 1 times 1 times -3 times 2 times -1 to the power of the number of swaps that we did. How many swaps did we do this time? In this example, we did 1 swap, right? So we got -102. So when we do an example here, and then we kind of feed into this. Let's call it A. Let's find the determinant of this. Well, this is enough to anger up the blood, right? Because this is sort of the opposite of upper or lower triangle matrix. So, any ideas on how to do this? Yeah.
Where do you swap everything from?
Okay, you're going to need to be a little bit more precise with it.
Swap the last row, the second row. Like pretty much like reverse it.
Right. So your idea, if I'm interpreting right, swap those two. Swap those two and swap those two. Okay, so. So the description here, besides more cowbell, is doing these swaps here. So now you put this on top and this on the bottom. And -1. Yeah. 3, 6, 2. And swap rows 2 and 5. And that was 0, 2, 3, 8, 7, 6. And then swap rows 3 and 4. And 0, 0, 0, 4. -1. Okay, so determinant of this. So it should be -1. How many swaps do we perform? We perform 3 swaps. And here, this is an echelon form, right? It's not real reduced, it's an echelon form. And the product of the pivots here, -1, 2, 1, 4, 2, 7. Yes? Right. And so this is -1 to 4, so it's going to be positive, and this is going to be 8 times 7 is 56, so that's 24. So this is a nice kind of alternative to being able to get a permanent link of layers. Let me give you a theorem here. So I'm going to give you a number of theorems. I'm going to kind of spell it out for you here. And then I am going to, I'm not going to go through really a hard book, but I'm going to kind of explain to you why these things are free. Theorem. So suppose we have an n by n matrix, then A is convertible. If and only if determinant of A. This is a fact about that we've known about 2 by 2 matrices for a while. Right? Now it's come full circle here because now we know this is true for every matrix of every size. And why is that? Well, this follows from the formula right here. If you have n pivots, then the product of the pivots is not 0. And what it means to have n pivots is you have n linearly independent rows in this matrix, so it's invertible. Right? And on the other hand, if it's not invertible, then you've got a missing pivot, but you've got more columns than you have pivots, and so it's not invertible. So that's good to know right there. Here's another theorem. The relationship between these two is their equal. The determinant of any matrix is equal to the determinant of its transpose. Anybody wanna venture a guess why that's true? Okay. Let's kind of look at a picture of this. If A looks like this. That's what A looks like. Then A transpose looks like this. Up there. And A 1, 2. A now to compare these, notice that you can get the determinant of A, you can expand across the third column, right? You get the determinant of A transpose, I'm sorry. You get the determinant of A, you can expand across the third column, right? Just this comes with subdeterminant minus this subdeterminants. Notice you can expand this about the first column and check to see that you get the same result, right? So that's kind of why that works, right? So the determinant of A and the determinant of AP are both the same. So corollary, and we already knew this, but A is invertible. It can only be a transpose. Because they have the same determinant. So if the determinant of A is 0, then the determinant of AP is, and if the determinant of A is not 0, then the determinant of AP is not 0. Okay. Any questions? And here's a big. And this is the last thing that I'm going to give you, but then we're going to get under the hood and try to understand this a little bit. A little fast and loose will be, but I'm going to try to. Suppose I have two square matrices. This is a fundamental theorem of matrix theory. Again, this is something that we already knew for 2 by 2 matrices, but it's true in general. Right? So the determinant of A times B is the determinant of A times and I might end up being a little circular here, but I just want you guys to kind of understand this. This actually, so let's get a little bit under the hood here, try to understand this. Try to look at the engine and see why it works. Let me ask you all this. So we had a theorem that said the following. Well, let's look at it. This goes a little ways, if you believe this in the first place, this goes a little way to explain how elementary row operation work, because suppose, I'm just gonna do a 3x3 example, so we can kind of wrap our heads around it, but. It's what I'm saying. Let me ask you this. If I wanted to multiply the first row by 5 and leave the rest of the matrix alone, right? That's one of our row operations. What matrix would I multiply on the left side? If I want to multiply the first row by 5 and leave the rest alone.
You have I mean, but there's five.
Like that. Everybody agree? And this turns this matrix into 5A, 5B, 5C, and the rest is the same. What does this do to the determinant? Well, we believe this. What's the determinant of this? What's the determinant of this matrix? It's 5, right? So if you believe this formula, the determinant of the new matrix over here should be 5 times the original determinant, which is exactly what we've got. What is what if I wanted to? What if I wanted to swap out the first and third columns? Actually, let's do first. What if I wanted to swap the first 2 columns? What would my matrix be? Leave the last one. Anybody? Yeah. Okay, it's the same as swapping the first 2 columns here, or the first 2 rows here. And I said columns, I never rows, sorry about that. Notice when I multiply this out, that takes DEF, and puts it to the top, takes ABC, puts it to the second, and then XYZ is left alone. Everybody okay with that? Yes.
Why isn't it a five?
What?
Why isn't it a five?
Because all I'm doing is swap, right? I'm starting over here and doing a different operation. What's the determinant of this? It's like -1, right? Which is what we get for swapping 2 rows. And finally, what if, I don't know, let's see, what if I wanted to A, B, C, yeah, X minus 2A, X minus 2B, X minus 2C. What if I wanted that to be the outcome of something times A, B, C, D, E, F, X? So really what I've done is I've taken the first row, or I'm sorry, I've -2 times the first row and added to the bottom. All right. Anybody know what this is going to look like? Yeah. Would it be like the -2 in the bottom of it? So. Right. -2 times the first plus the last. Everybody okay with it? What's the determinant of this matrix? It's lower triangular, so it's 1. Right. So this is again, it's sort of why if you believe that last theorem about the product of the determinant being the determinant of products, then you have to kind of believe what we said about the row operations not changing the determinant. Okay. Let me make this first observation that will be useful later. In my matrix form So what I'm doing here is actually. So what I'm gonna do is I'm going to find. T of x, the determinant of this matrix, A1, A2, AJ minus 1, X. CJ plus 1. So what I'm doing here is I am letting all these columns here be the same, they're all fixed. And this one can vary. This is like a variable, right? So T of the vector X is I input this vector as the J column of this matrix, and then I go to the determinant. So I can let this vary. By the way, let me ask you a question. What happens when I plug in the zero vector? Anybody tell me? You get zero, very good. Because what happens is if you plug in zero for this, that means that now you've got a square matrix with a column of zeros. That's got determinant zero, right? And so when I plug in the zero vector, my outcome is the number zero. This T is a linear transformation, Rn R. And it's a rather important kind of one. Notice my input is an individual vector. My input is that entire column. My output is determinant. It's a number. Right? So in other words, what do I mean by this? Why is this true? Well, what happens when I replace X with C times X? We'll just expand this along this column, right? And you've got a multiple of C's here. If you expand the determinant around this column, basically you're multiplying the determinant by C. So there you go. And it's also the case that T right, it's a linear transformation. Because if I replace this yellow X with X plus Y, just look at all the coefficients, or just look at all the inputs in this column and expand this around this column. And basically, the cofactor expansion gives you exactly what you want. So this is a linear transformation. And this is actually going to help us a little bit because so why do row reduction operation first? As stated. Well, number one, the ith row by the multiple K, well, single place multiple. If you multiply the ith row by K, it works very much this, let's row order column. Then you have multiplied that expansion by I row. So if you look at the cofactor expansion along the ith row, when you've got a k multiplying everything, you can pull that k out and it just multiplies the whole thing. Okay. Number two, here, you swap two adjacent rows. The sign changes. Now, notice I said adjacent here, and not each of the rows, but I'm gonna explain each of the rows. If you swap two adjacent rows, then the sign changes. Let me give you an example here. Again, this is the cofactor, because what happens is determinant of A is A11, C11, that's A12, C12, A13, C1. That's the cofactor. Now, if you swap two rows, two, the determinant of this, we'll call this S for swap. A11, C, right, so it's A11. In this case, it's cofactor 1, 2, plus A12, cofactor 2, plus A3, and remove it. But notice that the matrices that you get, right? For example, first cofactor is this matrix here, and your cofactor here is the same matrix, right? Because all I've done is now you're removing the row in this column. So you have to get this, but the sign is different, right? Because actually, sign down here is now negative, right? Because remember how the cofactor is. Determined. Right. And so when you move, what we've done here, when we expand in this way, is we've actually increased its row number by 1. So that actually changes the sign of all the cofactors. Now, okay, so that's okay if they're next to each other, but what happens if I swap two rows that aren't next to each other? Well, suppose I wanted to swap row 1 and row 3, say, suppose this is a 3-row matrix. How do I swap row 1 and row 3? Well, I'm going to do this adjacently. Now I'm going to get that all the way down here. And now I'm going to put the R3 at the top. So it actually took me 3 steps to swap row 1 and row 3. I agree with that. Swapping these two that were next to each other and these two that were next to each other. So -1 +1 -1. So it's again, in fact, you can show that if you swap any pair of rows, you have to do an odd number of exchanges to do it. Okay, any questions? Yes,
Why do you do that?
what?
Why do you do that?
Because what I'm trying to do is justify the fact that if you swap in two rows, it only changes the sign. And so to swap the first row and third row, I had to go through a sequence of 3 swaps to do it. So that's minus plus minus. Finally, for the last one, we could use this linear transformation for, and actually, I think I'm gonna get that a miss. So what we have is I sort of explained why it's the same for the row replacement, but you can also use that linear transformation from R into R that we just did as well to show that. And if you've got any questions, let me know. We can go through that. So what we have is the following. If E is an elementary row operation matrix, and let me tell you, let me remind you what I mean. In our previous examples, something like this, where it multiplies the first row by 5, or something like this, where it swaps the first and second rows, or something like this, where it multiplies the top row by -2 and added the bottom. These are kind of prototypes of these elementary row operations. Then what we've shown in all this is that determinant of E and F, determinant of A is E is row replacement. Matrix. K times determinant of A if E is multiplication, and -1 minus determinant of A if E is rows. A single row. So in particular, this is determinant of E. Determinant of A. So this multiplication works just for a single elementary matrix. So let me give you the big determinant of A, determinant of B. Okay, so let's do a quick kind of sketch while this is true. Number 1, if A or B is singular, then so is determinant of B. We've actually shown this earlier in class, but so is AB. So the formula works. If determinant of A or determinant of B is equal to 0. So if one of these is equal to 0, then that means one of these is singular, so AB is singular, so that has determinant 0. So there you go. It's easy when it's 0. When it's not 0, Now suppose. A is not singular. Then what can I do? I can reduce it to the identity matrix by a sequence of elementary row operations. Agreed? So another way to do this is there's a sequence of these elementary matrices times the identity, which is equal to X. And now we've got it, because if you look at A, B, this is EK minus 1, E2, E1, B. And if you successfully use this formula right here, this thing right here is determinant E, determinant B, determinant E2, E1, EB, and so forth and so on. And so you have determinant of AB is determinant of E1 or EK, determinant E1, determinant B, which is determinant. We're going to put these all back together, all in one step. Equal determinant of A. This is a big formula that hopefully you will find useful. Any questions on this? Right before class today, I made your next quiz active. It will be due Tuesday at 5 o'clock. I actually gave you 2 hours on it, because I just want to make sure that it's all safe and comfortable. So it shouldn't take anywhere near that much time. So anyway, any questions? All right, y'all have a good week. We'll catch you all on Wednesday.